Algebra 2, Chapter 2, Section 2, the Distributive Law. The distributive law is a law which allows us to distribute multiplication over addition. You can remember this law by thinking of the a, whatever it is, distributing over the multiplication like this. And you get a times b plus a times c. For example, we could distribute 6 times s plus 3w. And using the law, we take 6 times s to get 6s, 6 times 3w to get 18w. Maybe a more concrete example would be 3 times 7 plus 2. We could apply this law to numbers, and we would get 3 times 7 plus 3 times 2. And we can use the distributive law across more than two terms by applying it repeatedly. So a distributes over, we could think of b and plus c being grouped together to get a times b plus c, and then a times d. And then we can distribute just the sub-expression to get a plus ab plus ac plus ad from a times b plus c plus d. So for instance, 4s minus 3t plus 4w, we can distribute the 4 over the parenthesis using the distributive law to get 4s minus 12t plus 16w. Or we could distribute abstract letters, a times the quantity b plus c minus d. So here we have a negative. Distributing over, we would get a, b plus a, c minus a, d. That kind of brings up the negative sign. What about if we need to distribute a negative? So we have a negative. What if it's negative 7 plus x? Well, we can use this principle. We can think of the negative as multiplying by negative 1. If we were just multiplying by negative 1, we use the distributive law to get negative 1b plus negative 1c, and then doing the multiplications, we get minus b minus c. So we can just think of the negative sign distributing over by itself. So we need to negate each thing. Minus 7 minus x. And let's look at example 3 in the book. It says express this expression minus, or the negative of the quantity c minus d minus the quantity d plus c. Well, first let's distribute this negative. So we'll have minus c minus times negative 1 times a negative d essentially will be a negative of a negative. So it'll be plus d. And then plus, and we need to distribute this negative, minus d minus c. And now we have addition everywhere. We can except for here, it should be plus negative 1. So we can write this as addition plus negative c. So we have negative c plus d plus negative d plus negative c. So we have d plus negative d. That becomes 0 because the number minus itself is 0. Negative c plus negative c will give us negative 2c. So you see this expression, while it had a d in it, the d went away. The value of this expression doesn't depend on d at all, just on c. And we could do a more complicated example to show that a value doesn't depend on one of its variables. n minus k, all of that cubed. So let's think about this. How do we simplify? Let's just think about inside the parenthesis with the outer cube. Distributing the negative, we get negative n plus k, all cubed. N minus n is 0, because the number minus itself is 0, which just leaves us with k cubed, which we can write without the parenthesis. And then it doesn't have an n, so we've shown that this expression's value doesn't actually depend on the value of n, just on the value of k. What about division? Well, we can distribute division by turning a division problem into a multiplication problem. Remember, division is the same as multiplying by the reciprocal. Okay, so if we have 2/3, that's the same thing as 1/3 times 2. So we can then turn a division problem like this, a plus b over c, into a multiplication problem like this, 1 over c a times a plus b. Using the distributive law, 1 over c a plus 1 over c times b, and then using this identity this way, which you might say is backwards, but remember this is if and only if. It's equivalence. Doesn't matter which way we go. We would get a over c plus b over c, which is what we have written here. Let's do an example. Example 5. Show minus x plus y over minus 3 is equivalent to x over 3 minus y over 3. Okay, erase some of this. To show that it's equivalent, we should write the reasons down as we go. So, starting on the left-hand side, we can think of this as a multiplication instead of a division. We could think of it as negative 1/3 times minus x plus y by this identity here. We could just write by division is same as reciprocal, multiplying the reciprocal. Now we need to do the distributive law. Negative 1/3 times negative x, which will be plus 1/3 x. So that's this part, and then distributing by the y, we get minus 1/3 times y, which gives us x over 3 minus y over 3. So this is by distributive law. And this is by the same principle here, but we could call it rewriting multiplication as division. Now, we need to be careful with the distributive law. Not every operation is distributable. Let's look at example 6 in the book. It says, are the two expressions equivalent? A, 10x plus y and 10x plus 10y. The answer is yes, these are equivalent by the distributive law. Using the distributive law, we can turn the expression on the left into the expression on the right. B, what about 2 times xy and 2x times 2y? So here it looks like we've attempted to distribute multiplication over multiplication. Are these equivalent? No. Consider x is 1, y is 1. Then we have 2 times 1 times 1. The left-hand side is 2. And on the right hand side we have 2 times 1 times 2 times 1, which is 2 times 2 or 4, which are not equal, so therefore it's not equivalent. So distributing multiplication over multiplication is not something that we can do. It's not equivalent. C, what about the square root of s plus t and the square root of s plus the square root of t? Now we've not talked a whole lot about square roots, but remember a square root is finding the number that we need to multiply by itself to get a square. So for instance, the square root of 4 is, what number do I have to multiply by itself to get 4? Square root of 4 is 2. Square root of 9 is 3, because 3 times 3 is 9. 2 times 2 is 4. So let's put in some numbers here. What if we have, let's try x is 1. And one, sorry, not x, we don't have an x. S is 1. And t is 2. So we'll have, or maybe we should pick a perfect square. T is 4. So we'll have on the left the square root of 1 plus 4, which is the square root of 5. And on the right we'll have the square root of 1 plus the square root of 4. Well, the square root of 1 is, what number do I have to multiply by itself to get 1? 1. 1 times 1 is 1. And the square root of 4 is 2. 1 plus 2 is 3. And 3 is not the square root of 5. We can apply the distributive law backwards to factor an expression. So up to this point we've been distributing kind of forwards, so to speak. We've been taking a times the quantity b plus c, distributing over, and getting a, b, plus ac. But these were equivalent things, so we can also go backwards. We can take ab plus ac and find the factored version where we have two factors. Factoring, whenever you see the word factor, just think multiply. Factor means two things multiplied. Now, going forwards is very easy because we just distribute over, we get a result. Going backwards is not so easy. Why is that? Well, think about this. 3x plus 4. If I do 3x plus 4 forwards, I get 3x plus 12. Now, if I don't have this on the left, and I'm trying to go backwards, I have to factor the 12. I need to think about what can I multiply together to get 12, where I can find a common factor with this first term. Well, 12 equals 3 times 4. So if I put 3 times 4 here, now I have a common factor that I can pull out and put in front to undo the distribution, 3x plus 4, by pulling the 3 out. So you can see going backwards is much harder than going forwards, which is why factoring is a challenge and the distributive law is not as much of a challenge. So if we look at example 9, it says take out the common factor in a 2x plus x times y. Well, here the common factor is the x. Taking it out, we get x times 2 plus y. And we just remember we can reorder this multiplication to get x times 2 to pull the x out. B. Minus wx minus 2w. Well, we have a w in common. Factoring that out, we get w minus x minus 2. But are we done? This negative is also common. We can factor the negative out as well and have negative wx plus 2. That's a little simpler. So let's do that. So when we're factoring, if we get one factor out and we find another, we can pull it out in the next step. So we don't have to do it all at once. If we miss something, that's fine. C, 12L m squared minus m squared. Well, it looks like we have an m squared in common. If we pull the m squared out, we have 12L. And what's left here? Well, we pull the m squared out. There's still sort of an implicit 1. We can multiply 1 by anything, and still have that thing, so minus 1. Let's also now look at example 10. Let's clear the page here. So example 10, using the distributive law to rewrite expressions. A, 6xy minus 2xz. So here we can use the distributive law to factor this equation. Sorry, it's not an equation, this expression. So this expression, using the distributive law backwards, we can find the common factors. There's an x. X times 6y minus 2z. But we still have a common factor here. There's a 2 and a 6. 6 is the same as 3 times 2. So we could write x is 3 times 2y minus 2z. And we have this 2 we can pull out to get 2x, 3y minus z. Let's skip to C. Minus 4x, y, z, minus 8xy. Here we have x and y in common, obviously, so let's pull them out first. Minus 4z, minus 8. We have the minus also, let's pull that out. Minus xy, 4z, plus 8. Why plus? Because we pull the minus off both of them, or all of them if there's more than 2. 4 and 8. Well, let's think. 8 is 4 times 2. So we can pull out another 4. Pulling out a 4, we get minus 4xy times z plus 2. Why 2? Because that's what's left when we pull the 4 out. See why I crossed the z? Now we can tell a z from a 2. And last, let's look at f. F says w squared times the quantity a plus 2 plus w times the quantity a plus 2 minus the quantity a plus 2. Okay, well here we have 3 things, but remember we can distribute 3 or 4 or 5. We can do as many as we want by the principle we learned earlier of repeated applications. And we can simplify the repeated applications into just one use of the distributive law. Here we're using it kind of, so to speak, backwards to factor, so we find the common factors. This a plus 2 is common everywhere. So we can pull the a plus 2 in front. It's in all the terms. We can pull it in front. A plus 2. And then what we have left is what was not pulled from each expression. W squared plus w. And here again, there's always a 1 left behind when there's nothing left. So we have minus 1 because we need something to multiply back by to come back. You can always check your work with any factoring problem by applying the distributive law forwards and being sure that you get back what you started with.